There are over 6,500 products in the Mitutoyo full product line of precision measuring tools, instruments, and equipment. With M3 Solution Centers strategically positioned throughout the United States, Mitutoyo America has the advantage to provide timely assistance to customers in order for them to become more educated in metrology solutions and gain a better understanding with application challenges. Mitutoyo America products can be purchased through a vast distributor network located throughout the United States.
Welcome to another Advanced Manufacturing Media webinar. Our presentation today is Illuminating the Objective of Vision Inspection. Hello, I'm Mike Anderson, Senior Editor at Manufacturing Engineering. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor today is Mitutoyo America Corporation. Mitutoyo America Corporation is a sales, marketing, and most importantly, a service organization that was established in the United States by Mitutoyo Corporation back in 1963. Mitutoyo offers turnkey metrology solutions and integrates measuring directly into manufacturing processes by way of inline automation. Our presenter is Mitutoyo America Corporation Vision Product Specialist Alan Sias. Alan has served in product management and field support engineering positions with the company for more than 13 years. Sias has more than 15 years of experience in the field of vision systems engineering. He's a graduate of the Illinois Institute of Technology, Chicago, with a degree in mechanical engineering. During the presentation, you will be able to ask questions using the Q&A box that appears at the right of your screen. Time permitting, your questions will be answered following the presentation. If time runs out before we can get to all the questions, we will make sure that answers are emailed to you. And another housekeeping point. When viewing webinars over the internet, it's possible for the quality of the presentation to be affected by the type of internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth at the time. If you experience difficulty, please let us know by way of that Q&A box. If you have questions about any other aspects of our webinars, please email me at manderson@sme.org. I'll rejoin you after the presentation with a few concluding remarks. Now here's Alan Sias of Mitutoyo America. Alan?
Thank you very much for that introduction, Mike. I also want to extend a welcome to all the attendees. Very much appreciated for joining this webinar today. I am Alan Sias, the Vision Product Specialist of Mitutoyo America. We thought it would be a great idea to go over the Vision product line. If you are interested in exploring vision solutions, we thought it would be nice to eliminate some of the mystery when you're trying to explore measuring vision instruments. So we came up with a clever title, Illuminating the Objective of Vision Inspection. So some of the items that we're actually going to go over today is just the basic image storage of a vision system. How do we use pixels for measurements, or the images that we're actually digitizing using that image storage system? How those pixel values show up as a grayscale in that digital image. And then that allows us to then do things like automatic edge detection, and then we'll go over some basic vision functions like autofocusing. And then we combine those data points to kind of together with a composite coordinate system. We'll go over that in detail. And then towards the end of the presentation, we'll cover some of the advanced vision functions. So this will go over what entails a basic vision image storage system. In this case, we're using a black and white CCD camera. This is what we're going to use to obtain the light coming through the system. And then any typical vision system would have some light source, whether it be LED or halogen. There's other things like fluorescence that could be used. But in general, you could have a light source, whether it be external or internal to the system. In this case, we're talking about an internal light source that's actually internal to the system, and we call this coaxial illumination. This will be light that passes through the main objective, and we'll see that here in the next slide. So you have something like an objective lens in the optical path. Here we have a light source, half mirror objective lens, and then some kind of workpiece placed on a stage. As we turn on the illumination source, it'll actually hit the half mirror, pass through the objective lens, hit the workpiece, and then return through the objective lens and pass through the half mirror. And then that image and light passes through the half mirror into the CCD camera. Once that image is actually captured by the CCD camera, it goes into the video signal. We actually amplify that signal, and we actually convert it from an analog signal to a digital signal, and then we actually use a frame grabber to display and actually do all of our processing of this image utilizing the PC. And then an image that we obtain, you'll see something like this. Now, we're using a rectangle here to sort of represent the pixels or the individual values that we're receiving from the CCD camera. And so the display signal will show or illustrate, in this case, a circle. So we just are sort of looking at a workpiece that's round in nature, and this would be the result on the screen. So looking at that, isolating that image of the circle, in this example, we'll use 640 pixels by 480 pixels. So this is our digitized image, and it's comprised of pixels, or an array of pixels. And if we magnify any area of the pixels, we have something what we see here on the left. You can see some of these squares are empty, or they have some value returned to it from the light that passed through that optical path that we described earlier. So we have some pixels that are gray, a little bit darker. Some might be completely black or completely white. So I just wanted to stop for a moment here and discuss why we care about pixels. We actually use pixels to perform measurements on an optical system. In this particular example, we have a 10 micron pixel size. And so what we do is actually take the number of pixels, multiply it by the size of the pixels, and that would, the result of that would give us our length. So in this particular example, we have 300 pixels with a pixel size of 10 microns multiplied to give us 3,000 microns, which would be 3 millimeters. So if we were measuring a piece or a part that was 3 millimeters, with the optical sensor, we could just count the number of pixels, and our result will be 3 millimeters. One other thing I want to mention here is also pixel size is actually a function of our magnification. So right now we're not describing magnification here. That objective lens that we covered a little bit earlier has a magnification associated with it, and so we could actually vary the pixel size based on our main objective lens or optical path. So I wanted to talk a little bit here about the grayscale. Now, we talked about the CCD getting a digital image, and what the digital image gets converted to is pixels of some value. And we actually use a multi-level grayscale, or it's actually a better method to use versus a two-level grayscale. If we look at the left picture here, this is just indicating whether or not the pixel is on or off. It's just going to be black or gray. So it's going to have black or white, sorry. And then we have a multi-level grayscale, where any given pixel could be at a value from 0 to 255. So each pixel that we capture on the CCD will be assigned a numerical value, and depending on what kind of CCD you have, you could have a situation where you have only a two-level grayscale result or a multi-level grayscale result. And so our image quality is much dependent on how many levels of grayscale that we're implementing on our CCD array. So here's an example of just using a two-level grayscale to display an image. Any one of these three images are displayed with a specific threshold value, and you can see as we move up and down in the threshold range, we're only capturing a low-level amount of detail within a given image. So this is kind of representing a part that we might be looking at. There might be machine marks, there might be some detail that we're missing if we're not using a higher segmented grayscale level on the CCD camera. Again, displaying 3 different images. As we change the threshold values, we capture different details, but not all of them. Okay? So this is just all dependent on the selected threshold on a 2-level grayscale CCD. On this slide, we're actually going to describe a little bit more why multi-level grayscale is a little better. On the left, we have, again, just the 0 or 1 pixel value, and you can see on the right image, we have much more detail. We could actually see where the mountains are located and that they are mountains, and the trees in the foreground, and it's a little bit more detail that we can make out. And this is very important when you're doing vision measurement. The more detail that you can make out within a given image, and we'll actually throw some terminology in your field of view, which is the area of interest in which the camera is located, the more detail we have, the better measurements we can make. So this is kind of going back to that circle that we displayed earlier in the presentation. If you can imagine, we have a circle here on the left image, and that blue line being the tool. We call these vision tools. And this vision tool is actually scanning individual pixels from the left to the right, and the graph below that is actually indicating what the value of the pixel is. In this case, it's saying the empty space is a value of 255, and you can see when it hits the edge, it actually drops off to some value below that. And so we could actually determine the transition point of the edge. So 1 indicating the scan start position of that tool, 2 indicating where the edge is actually detected, and then 3 being the ending of the scanning position of that particular tool. So if we actually looked at the individual pixel values here on the chart on the right, and looking at that middle row, you can see the values are averaging in the 200s, 240 to 200. So we have 243, 244 going across, and then that red area is indicating where the edge transition occurs. And then it sort of drops off into where the material is on the workpiece. Each pixel is assigned a numerical value, and these are the values on the grayscale. So we still have some indication of where the edge transition occurs, but we don't really know if it's at the beginning of this transition or at the end or somewhere in between. So again, on the next slide, we're actually to go over a little bit more how we're doing sub-pixel edge detection, but here you can see this is the edge transition for a specific vision tool. There's also other various tools that can be used. There could be things like circle tools, arc tools, line tools. We're just picking the simplest example here where we're doing a single row of pixels. So following the same example of that circle and that little area of interest, that circle that's on the tool, if we look at the right side, you can see a blown up image of how it would occur or appear as we digitize the image that we're getting on that CCD. As you notice, you get some pixelization of the edge, and so there's some transition point, but the pixels, each pixel has a value on that transition point. And if you look at the chart below, we're actually drawing these rectangles at the height of the grayscale value along the tool position that we're scanning. And the column that's actually highlighted is what we might consider the transition point or the pixel at which where the edge occurs. And then the question might arise, well, how do you know if you're at the beginning of the pixel or at the end of the pixel? In this particular case, without interpolation, we could be off by the entire pixel, in which case, if this was the value of our original example, it would be up to 10 microns error, which in a lot of cases is unacceptable for vision measurement. So how do we perform subpixelization on an automatic edge detection tool using vision? On this left side, we have the same rectangle that we saw previously, and this is without using any kind of subpixel processing. So we actually take the digital signal that we receive from the CCD camera, and fit an analog curve to those rectangles. And so by doing so, we're actually splitting the rectangles into a sub-pixel processing, which again, all this is working the mathematics out on that frame grabber board. So this analog tool, or the analog curve within our tool position, are actually splitting these so we can determine where the edge might occur. So we have a slope here, and we actually measure based on what we call thresholding. And that edge will be detected somewhere in between these analog curve based on the mathematics we apply in our software. And then the next section here just shows the analog curve fit through our linear curve. So because we can actually create a digital image, and we know the size of the pixels, and we're actually able to determine where edges occur. Some of the basic vision functions that we can actually perform on an optical system are the automatic edge detection, right? We can determine where an edge occurs in the XY plane. We also can measure how sharp and contrast these pixels are and perform what we call autofocusing. So this would be something where the system would be moving in a z-axis, and as the slices that are obtained from the CCD camera, we're analyzing each slice as we're moving up and down. We can determine the focal point very accurately. We can also do some other fancy things like pattern recognition. I can compare an image to another image because my vision probe can actually see what's on the screen and compare pixels to a known image. We could use that maybe for determining alignment, determining position of features, even checking whether or not the feature exists. So we're actually going to play a video here to show you just some of the basics that we talked about. This is actually doing some autofocusing, automatic light adjustment, and then it very quickly measures by a scanning of an arc tool here on a circle, and we're actually combining those data points. This is an arc tool, a line tool, arc tool, line tool. And we're very quickly processing results. We can see it graphically. We're also getting text-based results here. So that's a generic program that is obtaining geometric type features. In this case, just some circles, lines, angles, and some positions. So I wanted to mention autofocusing again because it's a little bit different than edge detection. On a typical system, you have your CCD camera moving, whether it be manual or automatic. We could actually move in the z-axis and, again, watch the pixel values as they change, and the graph on the right indicates when we are actually in focus. So the vertical column is explaining our z coordinate, and the horizontal is the contrast value on the pixels. And so as we move up and down in the z-axis, we actually find a peak contrast, and this is where then the z coordinate comes into play. When we hit the peak contrast, we have a z-coordinate associated with where that particular frame is maximum focus. Similar to a digital camera, this is just doing it on a little bit of a higher level. Here's another example of how that graph might look. On the left, we have edge contrast due to an autofocus edge. And as we went more and more extreme autofocus, this chart on the bottom would eventually be flatline. This is just revealing we have a low signal, indicating low sharpness, low contrast, and we know that we're out of focus. On the right here, you have edge contrast, and we can see with our eyes that it's in focus, and the contrast chart as well is also peaked out. So when this, again, peaks out, we know what the Z height or Z location of that particular frame is. So another thing I wanted to point out for a basic function is how are we measuring circles that might be larger than what we call the field of view. So each of these locations where the blue arrow is surrounded by a rectangle on the left-hand side. And I just label these as 0.1, 0.2, and 0.3. The arrows are the larger arrows going around the circle are indicating the machine motion. And so if we look at this carefully, we're actually measuring a point in field of view 1, measuring a point in field of view 2, and measuring a point in field of view 3. And even though that features might be larger than the camera's capability, we can actually combine these data points to form geometric elements, whether they be points, lines, circles, angles, and things like that. So just to elaborate on that a little bit more, then we start getting into our composite coordinate system. Following along the same example, we have machine motion measuring 3 points in 3 different field of views. And so what we call this is actually what we call a vision coordinate system. Each one of those field of views will have a coordinate system associated with it. When we're trying to measure a point on a particular edge, we can assign coordinates, what we call Vx or Vy, where that lies within that video coordinate system. So the crosshair at the center of the video coordinate system would be 0, 0, and we would have some value offset from the center of the crosshair. The center of the crosshair is basically the center of our camera location. And we would take that two-dimensional plane and put it into 3D space. So I'm just going to repeat that. The left image is a video coordinate system, which is, again, our camera, which is a two-dimensional sensor. And we're going to take that plane and put it into our machine coordinates. And so the result of that is we have a combination of video coordinates and machine coordinates. And then we could just designate the machine coordinates by m sub x, m sub y, and m sub z. And so the measurements that we actually obtain within space, the vision coordinate system in combination with the machine coordinate system create the real location of the point. And just to restate that in a format, to get the x coordinate, you would add in the machine sub x plus the vision sub x to result in your x coordinate. And same thing for y. And z is a little bit different because we have a two-dimensional plane residing in a three-dimensional space. And so we only care about where the machine z is when we make that measurement. So with that in mind, we have the ability to do some advanced optics. And this is just going to illustrate what we call points from focus. We're just going to set a high point and a low point in which the system is actually able to scan in the z-axis and build a three-dimensional topography of what we see in this video window. I would actually like to play this video twice when I describe this, but you'll see the result of a hemisphere building a three-dimensional topography. So I want to go back all the way to the beginning of the presentation to describe. We have the ability to capture pixels with the CCD, given the proper illumination. We know when things are in focus. We know the size of the pixels. We also we know when they're in focus. And so by combining all of this these principles for doing vision optics, we're actually able to achieve a topography within a given field of view. We also have the ability to stitch multiple field of views together, as well as capturing many data points. So in this example, this would result in about 300,000 data points per field of view, using all of these optic principles that we talked about here. So I'd like to actually hand this back over to Mike and follow up with some question and answers.
Hi, this is Mike Anderson joining you again. Thank you, Alan, for that informative session. We did indeed receive some questions, and it would be nice to get to all of them before our time is up. All of you out there do remember, however, that if we do run out of time before addressing every question, those unanswered questions will be forwarded to Mitutoyo America, and a response will be forthcoming. Right now, it looks like we have plenty of time, though, so let's get to the questions. Alan, let's start with this one. And the question is, how would I determine if a visual system is right for my application? Or if it can even measure accurately enough to meet my customer's requirements?
Well, vision platforms are very dependent on their design. And so things like what kind of illumination is being used, what are the smallest features that can be resolved with a given optical path. Some are better than others. It also depends on the magnifications you can achieve. And even comes down to when we're talking about a composite coordinate system, when you're combining data points with two different elements, one being the optics or the vision probe, and the stage accuracy, would give you a relatively good indication of what the accuracy may be. Typically, well, it depends on what machines you're looking at, but typically 3 to 5 microns is in the range of a standard vision system, and then from there it actually can get much better. 1.5 microns, somewhere around 1 micron, and then some of the really high-end machines could do about 250 nanometers. Depending on what types of measurements you're also making. For example, at the end we showed a video called Point from Focus. That's a little bit less accurate. For example, the repeatability is about 1.5 microns, where on a vision system that has high resolution scales where you're combining data points as you're moving the stage is kind of a critical issue. A lot of times when you're trying to determine a vision system, the number one thing you need to look at first is whether or not you can image the material properly. Although as time has gone on with vision systems, the resolution or the fidelity of the images have increased quite a bit. And so that's not as much of an issue. And there's also other ways of detecting edges, not necessarily whether or not we have a big drop-off in the signal, but since we're always looking at pixels, there's other algorithms that can be applied to find the edge. One example might be, there's not a whole lot of contrast for the edge, but there might be a texture difference or a difference in color. And so it really depends on the application of what you're trying to measure. I mean, we've been in a lot of different industries. It's hard to nail down a specific industry. Optical has been used in automotive to medical to electronics. And vision also has the ability to do full three-dimensional features. A lot of times, the difference between picking a tactile type machine and a non-contact is either the features are too small and you can't measure them with a tactile probe, or you need a higher level of throughput. It really comes down to whether or not you can image it, if you need the speed, and how accurate the base model is.
Okay. So I think it's probably safe to say that if somebody wanted to get in touch with you guys with a specific example of what they're looking for, I'm sure somebody at Mitutoyo America Corporation could help them out. Is that right?
That's absolutely right.
Okay, good. Let me go on to another one here. And the question begins with a comment, and it says, we went over that last slide rather quickly. Can you elaborate on how you can achieve optical scanning? We have a chance to revisit that.
Yeah, so earlier in the presentation we discussed the basic parameters required, things like measuring pixels or getting values from the CCD at the grayscale level. There's also a few other things that go into that to achieve the optical scanning. Two of the most important things would be the way we actually achieve it is by calibrating or compensating for the stigmatism in any given objective. We could actually map out the aberrations, or they have geometric aberrations that are associated with any given lens. Each one's a little different. And so that lens needs to be mapped out, and so that we can do what we call points from focus accurately. And the second thing is when you're measuring anything with a texture, if you rotate that texture beneath the camera, you're not changing anything you're measuring, you're just rotating that image. You actually get a sign error. The Z height changes slightly. And part of compensating for that is key to being able to do optical scanning. As well as we leave out some data points around the border, what we call a margin of error. And basically that's a little bit more than we've talked about here, 2 more parameters that need to be achieved. And also the base model, again, is important. If the base model can achieve high accuracy Z scanning, that also will help you achieve optical scanning.
Great. Okay, here's another one. This is a very good question. Now that you've measured all of those features, what can you do with the results?
Okay, so after you optically scan something, you achieve a topography or a 3-dimensional model of the results, maybe resulting in 300,000 data points per field of view. You could actually take that point cloud and do some kind of analysis on it, whether it be a wear analysis from one point cloud to another. You could actually do a volume analysis. You could even break down the 3-dimensional topography into 2-dimensional slices. So if you had the 3-dimensional topography, you could actually run a line down the middle of it, essentially cutting it in half or sectioning it, and then looking at it on its side. For example, that ball grid array or that hemisphere that we looked at, we can measure the radius at the top, the height of the ball grid, and maybe the diameter.
Okay. We might be going over some of the same territory because the next question is, you showed a vision system measuring a diameter. Can you give other examples of what can be measured?
So I did briefly mention we had an example of a circle. You can do lines, points, and even extend that out further to 3-dimensional shapes like cones, planes. We could do flatness on the planes, as well as most of the GD&T callouts, so true positions, concentricity, perpendicularity, parallelism, and we are talking about vision measurement here, but you also have the ability to put what we call multi-sensor together. You can do scanning lasers or touch probes to achieve another level of measurement on top of the vision platform.
A plethora of options.
Yes, that's right.
Okay. Here's another one. What are the important considerations when purchasing a vision system?
So when you're actually purchasing a vision system, back to our first example, talking about the optical path, again, it's important to consider the light sources. Some machines have limited light sources. Some have a lot of options. One being coaxial or stage light. Things like that are actually important. And again, whether or not the optics can support high resolution. If you're looking at something that's on the order of 10 microns as a feature size, the system has to be able to achieve that kind of level of magnification to get down to that resolution. One of the limiting factors might be the objective lens itself and how well it's able to transmit the light that we talked about in this webinar. As the light goes through the objective, you're going to lose some of that signal. And so if your numerical aperture value on the objective lens is low, it's going to be a limiting factor in that optical path, and you won't be able to resolve features that are that small. So that's two of the components. Some of the other things you might want to consider is the software. What kind of functionality is the software bringing to the table as far as, again, the geometries that you're measuring? How accurately can it measure 3D space? And then what are we doing with that data afterwards? If you have 7 million data points that you've collected through something like points from focus, or even doing a scan with normal edge detection. You have to be able to process that amount of data. And so that's going to be also key is, how are you going to be able to process that magnitude of data easily? Some systems will actually slow down and chug, and you can't really get anywhere with that data set.
Okay. Well, I think, Alan, we're gonna wind it up here. And for those of you listening, again, a reminder that, as promised, all unanswered questions will be passed along to Mitutoyo America, and you can expect a reply by way of email. Also, keep in mind that this entire webinar will be available for replay by 4 p.m. Eastern Time, and you can access it by using the same sign-in link you used earlier. Now, beyond our webinar series, SME and Advanced Manufacturing Media have a host of ways to keep in touch with the latest developments in manufacturing. For instance, the September 2005 issue of Manufacturing Engineering included a featured article on measurement and inspection called Metrology Gets Connected, which you can find on our website. Also, the upcoming February 2016 issue of Manufacturing Engineering will have a feature article on metrology for medical. And of course, Advanced Manufacturing Media continually delivers the latest measurement, metrology, and quality news at our website, which is www.advancedmanufacturing.org. Thank you all for joining us today. We hope you found the presentation informative.